The first definition that we are going to look at is the definition of a normal series. A normal series of a group G is a chain like this of normal subgroups of G. Okay, so it's a chain like this, as you can see from the page, and all of these G0, G1, G2, G3 up to so on, all of these are normal subgroups of G. And let me tell you that this is the only difference between the normal series and a subnormal series. In subnormal series, you just need to have that G0 should be a normal subgroup of G1, but it is not necessary to have G0 as normal subgroup of G. But in normal series, you should have G0 as normal subgroup of G as well, right? So from here you can conclude that every normal series is also a subnormal series, but converse is not true. And then we have some examples of normal series. Here we have an example of a normal series of S4. This is a normal series of Q8. This is the normal series in D4, right? And another note that we must look at is that a group can have multiple normal series. Okay, so if we look at this series, it is not the only normal series of the group S4. There can be other series as well, right? Okay, so next we are going to look at the definition of a composition series. Okay, so a composition series of a group G is a normal series but without repetition, that is proper inclusion of subgroups like this, whose factors are all simple groups. Okay, that is they have no proper normal subgroup. Now what does it say? Let me explain it. Now it says that composition series is also a normal series. It's not something new, but we are implying one more condition, actually two more conditions. Number one condition is there should be no repetition. Repetition is not allowed. And what does that mean? In the definition of normal series, if you look back and by stopping this video and go back, you will see that I have used the sign, a line over here at every step. And what does that mean? That G0 may be exactly the same group as G1, okay, which is actually a process of repetition, but it is not allowed in composition series. The inclusion should be proper, right? G0 is proper normal subgroup of G1. It cannot be equal to G1, right? And the second condition in composition series is that the factors group that are being formed, if we look at this for example, so the factor group over here will be G1 by G0, and if we look at this inclusion, then the factor group will be G2 by G1. All of these factor groups should be simple groups, and I'm assuming that all of you are aware of the definition of a simple group, and if you are not, then you can see from here they have no proper normal subgroups. A simple group is simply a group which does not have proper normal subgroups. Okay, it only have trivial subgroup and the group itself, right? So here is an example of a composition series, and this is a composition series of S5, the symmetric group of degree 5. Okay, so you can see that trivial subgroup is normal subgroup of A5 and A5 is normal subgroup of S5. And if you look at their quotient, it's very obvious, it's very clear, you can prove it very easily that they are simple groups. Okay, the factor groups, the first factor group will be A5 by the identity subgroup, right? And the second factor group will be S5 by A5, right? So both of these subgroups, both of these factor groups I should say, are simple in their nature, right? And the next preliminary concept that is needed for proving Jorden-Holder theorem is that every finite group has at least one composition series. Okay, or you can say every finite group has composition series. Now this is a result, it has been proven in some books as well, so you can prove this as well by using mathematical induction. I'm leaving it for you people. The next concept that is necessary for us to learn before going to prove of the Jorden-Holder theorem is the equivalence of normal series. Okay, as I have already mentioned that a group can have more than one normal series, right? So let's suppose that we have a group G which has two normal series. First is this, second is this, right? So we will say that these two series, normal series of the group G, are equivalent if number of factors of both series are equal. Okay, first of all, the number of factors. First factor over here will be G1 by G0, then we will have G2 by G1, and so on. Here we have Gn by Gn minus 1. Similarly, in this series we will have factors h1 over h0, then of course h2 over h1, and over here we will have hk over hk minus 1. So the number of factors that are being formed here and here should be equal. Okay, this is the first condition. The second condition is that if you form a set of factors of this series, I have written it like here, and if you form a set of factor groups of this series over here, these two series should be these two sets should be in one-to-one correspondence, and the corresponding factors should be isomorphic. Okay, so this is the definition of this is how we decide whether two series are equivalent or not, right? So here I have an example for you, and in this example I have given you two normal series of the D4 group. One is over here, the other is here, and I am leaving it for you to verify that these two these two normal series are equivalent. Okay, I'm leaving it for you. And the next result that we are going to look at is that product of two normal subgroups H and K of a group G, we write it as HK, is again a normal subgroup of G. Also, H and K are normal subgroups of HK as well. This is also a result that we will need. And then we have the second isomorphism theorem. All of you are quite aware of this, which says that let H is a subgroup of G and K is a normal subgroup of G, then H by H intersection K is isomorphic to Hn over N, right? Another note that we are having here is intersection of a subgroup H and a normal subgroup K of a group G is normal subgroup of both H and K. I'm actually trying to emphasize here is that this H intersection K is normal subgroup of H as well as normal subgroup of K. So these were the results that we needed before going to prove the Jorden-Holder theorem. So let's start with the statement of the Jorden-Holder theorem, right? So the statement is that any two composition series of a finite group are equivalent, and I have written here the explanation of this wording. If you have a non-trivial group G which is finite, and you have two composition series of G like this, right? One is containing the normal subgroup Gi's and the other is containing the normal subgroups Hj's, let's say. Okay, so if these two are the composition series of this group G, then there is a one-to-one correspondence between the set containing factors of this series and the set containing factors of this series, such that the corresponding factors are isomorphic, right? So this is what we need to prove. Okay, so let's start our proof. Ladies and gentlemen, we are going to prove this theorem by induction on the order of G, right? Also, we will use the symbol tilde to denote R in one-to-one correspondence, right? So from now on, whenever I use this symbol between any two sets, it means those two sets are in one-to-one correspondence, or you can say there is a bijection map between them, right? So let's start with our base case. The base case is when the order of G is 1. It means that G contains only the identity element and the result holds trivially. Okay, now suppose the order of G is greater than 1 and the statement holds for all groups of order less than the order of G, right? This is our induction hypothesis. We are assuming the order of G to be greater than 1, and also we are assuming that this statement, the statement of Jorden-Holder theorem, is true for all groups of order less than the order of G, right? So there are two cases arise from here. If I take you on the previous page, or leave it, it's okay, no problem with that. In previous page you have seen that the second last group in both series, one of them was Gn minus 1 and in second series it was Hm minus 1, right? So there can be two possibilities. Either these two groups are equal or they might be different. Okay, so first we assume that these two groups are equal. So if you take these two groups to be equal, then you have actually two composition series of this Gn minus 1, right? One is itself the GIs of the series which contains GIs, and the other is which is being formed by HIs, and it ends at Hm minus 1, which we have taken as Gn minus 1. So we have two composition series for the group Gn minus 1, right? And also we know that the order of Gn minus 1 is less than the order of G. As you can see, order of Gn minus 1 is less than the order of G, and induction hypothesis tells us that every group with order less than order of G should have equivalent composition series. So what we have mentioned in the previous page, the two series of Gn minus 1, both of these two series are equivalent. And what does that mean? It means the factor groups of first series of Gn minus 1 and the factor groups of second series of Gn minus 1, if we form their sets, those two sets will be in 1-to-1 correspondence, such that the corresponding factors will be isomorphic, right? So what we are going to do next is that appending the same group Gn by Gn minus 1, which is obviously Hm over H minus 1, Hm minus 1, both of these two groups are same. How? Because Gn and Hm are same, and Gn minus 1 and Hm minus 1 are same by oversupposition. So what we are going to do is we are going to write over here Gn over Gn minus 1, okay, and over here we are going to write a next element Hm over Hm minus 1, okay. So we have these two sets, and of course these two sets are still in 1-to-1 correspondence, and all of the factors in this all of the corresponding factors are still isomorphic. And how are we sure about that? Because all of these factors were already isomorphic to each other, corresponding factors, and what we have done is we have introduced a same element in both set, and that element will be in 1-to-1 correspondence, such that both of these are isomorphic because they are same groups, right? Such that all the corresponding factors are still isomorphic. Hence the result holds if Hn minus 1 and Gn minus 1 are same. Obviously, if you have closely looked at the series that we have written for the two composition series that we have written for G, one of them was containing these factors and the other was containing these factors. So we have proved that all the factors in this set, factor groups, and all the factor groups in this set, they are equal in number, right? Also they are isomorphic to each other, so these two composition series are now equivalent, right? So we have proved this result for when Gn minus 1 and Hm minus 1 are equal, okay. So now we move on to our next part, where we are going to suppose that Gn minus 1 and Hm minus 1, they are not equal, right? So let's suppose that Gn minus 1 is m and Hm minus 1 is n, right? Also let k is equal to m intersection n. So we are taking the intersection of Gn minus 1 and Hm minus 1, which we have named as m and n respectively, right? As k is finite, how do we know that? Because the group G was finite, so there its subgroups Gn minus 1 and Hm minus 1 will be finite, and if Gn minus 1 and Hm minus 1 are finite, so their intersection, which is k, will also be a finite group, right? So it has a composition series. How do we know that? because in our preliminaries we have studied that every finite group has a composition series. So this K will also have a composition series, and that composition series is written over here like this. Okay, now as M and N are both normal subgroups of G, so their product Mn will also be a normal subgroup of the group G, right? Also, M and N are normal subgroups of Mn. Both of these things have already been studied in our preliminaries, right? So what do we have? We have M as normal subgroup of Mn, as you can see from here, and Mn is a normal subgroup of G, right? So we have actually introduced another normal subgroup of G, I should say a proper normal subgroup of G, which contains properly this M. But if you look closely, is this possible? No, it is not possible. How do we know that? Because we have already studied that G over M is simple. And how do we know that? Because if you can remind, M is Gn minus 1, which was the second last subgroup which contained in the group G. There was no you can say kind of group between them. So G by M was simple because of the definition of the composition series. So there can be no normal subgroup of G which contains M properly. Okay, I have written it over here. There can be no normal subgroup, no proper normal subgroup of G which contains properly M. Okay, so now there are two possibilities. Either M is equal to Mn, right, or Mn is equal to G. So if you take Mn to be equal to M, then N will be normal subgroup of Mn, which is equal to M. What does that mean? It means that there is a normal subgroup M between N and the group G. But again, that is not possible. Why? Because G by N is simple. So if you are taking G by N to be simple, then there is only one possibility left, that this M and N are equal. But this is not possible because we have already supposed M and N to be not equal, right? So what is left for us then? If this is not true, then this Mn is equal to G. Okay, and then by using the second isomorphism, I want you to forget these sides and look at these two sides between them. So M over M intersection N will be isomorphic to Mn over N. Okay, this is by second isomorphism theorem. Similarly, you can write N over M intersection N is isomorphic to Mn over N. Okay, and then you can use the simple notation Mn, as we have proved, is equal to G. So we replace it with G. N remains same, यहाँ पे M remains same, and M intersection N is K. Okay, similarly Mn is being replaced as G, M is remained unchanged, N remains unchanged, and M intersection is written as K. Okay, so now keep this in your mind. We have successfully proved that M over K, this factor group, is isomorphic to G over N, and N over K, this factor group, is isomorphic to G by M. We are going to use these in our further discussion, so keep this in your mind. Okay, now the group Gn minus 1 can have two series. One was the series which we have mentioned in our statement of the theorem, which was containing Gi's. The other can be through K. Why? Because K was a normal subgroup of M, which is Gn minus 1, and K has its own composition series. So the group Gn minus 1 has two composition series, and since its order is less than the order of G, so by induction hypothesis, the factor groups formed by this series or by this series, they will be in one-to-one correspondence, such that the corresponding factors will be isomorphic, right? And using this similar argument, we can also write that the factor groups H1 over H0, H2 over H1 till Hm minus 1 over Hm minus 2, the set of these two factors, and the set of factors K1 over K0, K2 over K1 up to Kt over Kt minus 1, and n over k. These two sets will be in one-to-one correspondence, and their corresponding isofactors will be their corresponding factors will be isomorphic, right? So this is our argument. Keep this in your mind. I am naming this as 1 and naming this as 2. And next, what we are going to do is I'm going to append a new group on both these sides. Similarly, I'm going to append one new group on both these sides. Okay, so just look at that. If we append g by m on the both sides of 1, we will have this statement, right? And if we append g by n on both sides of the 2, we will get this, and I'm naming it as 4. This was named as 3, this was named as 4. Now I invite you people to have a look at the right side of this tilde and this tilde, right? So you can see very clearly that the first groups, factor groups from k1 over k naught to kt over kt minus 1 are same in both 3 and 4, on right hand side of both 3 and 4. There is only one problem, and that problem is about these 4 groups. If these 4 groups are in such a way that these 2 groups and these 2 groups are in one-to-one correspondence, and somehow they are the corresponding factors are isomorphic, then we will be able to successfully prove that the right hand side of 3 and the right hand side of 4 are equivalent. Okay, so how do we do that? If you can recall, we have just proved on our previous pages that m over k was isomorphic to g by n, and g by m was isomorphic to n by k. Where we have proved this? We have proved this when we use the second isomorphism theorem. Okay, so this helps us to reach at this position where we have these 2 elements in one set and these 2 elements in one set, and they are in one-to-one correspondence such that the corresponding factors are isomorphic. So the right hand side of 3 and right hand side of 4, these two these two set of factor groups are equivalent. So if these two are equivalent, then their left hand sides will be equivalent as well. So from here we have, this is the left hand side of 3 and this is the left hand side of 4. So finally we have proved that this set of factors and this set of factors are in one-to-one correspondence such that the corresponding factors are isomorphic. Okay, and if you look at these two set of factors closely, you can observe very clearly that this is the set of factors of first series of the group G that we have mentioned in the statement, and this is the set of factors of second series of the group G. So we have proved that if Gn minus 1 and Hm minus 1 are not equal, still these two series, the composition series of G, will be equivalent. So this completes our proof for Jorden-Holder theorem. Thank you so much for watching the complete video. Please like and share this video, subscribe my channel, hit the bell icon so that you don't miss any update in the future. Thank you so much.